Hi everyone, this is our IoT project. We developed Share2Care, a platform for smart health aiming at meeting the needs of patients with some selected diseases. From our point of view, the patient is the center of the platform. That's why, first of all, we would like to present you the hardware components that we used, which are required to get the information about the physical situation of the patient, which is the base on which our services have been developed. There are 4 health sensors. Starting from the right side of the screen, you can see a scale, a pulse oximeter, a blood pressure sensor, and a glucometer. Then there is an Arduino Leonardo with an heart rate monitor sensor by DF Robot, a button to start the acquisition, and the Raspberry Pi 3 that we used as a server and a broker for our communication protocols. The base of the entire platform are the data coming from real world. As we said before, the hardware involves 2 different types of sensors. The iHealth Smart sensors, whose data can be retrieved through the iHealth Cloud, and the ECG analog sensor, which allows to acquire an ECG signal thanks to an Arduino Leonardo. In both cases, data are sent to the user PC, since Arduino must be physically connected to it through USB, and the iHealth Cloud communicates through REST protocol with the user PC in order to allow him to grant his permission to the data usage by the Share2Care platform. The user PC then posts the new data on an appointed port on localhost, so that Raspberry Pi is able to get them through REST communication protocol. So at this point, Raspberry Pi becomes the center of the whole architecture and it has to send the new data to the correct microservices. Here the communication flow exploits a publish-subscribe approach thanks to MQTT protocol. To each type of data has been associated as a specific topic, so when a new data arrives to it, Raspberry Pi publishes it under the right topic to the message broker inside itself, which is in charge to forward them to whatever microservice has subscribed for that topic. At microservice level, data post-processing takes place in order to extract from raw data some further knowledge about the patient's status and use it to offer the patient a service. Each microservice posts the processed data on an assigned port in order to add it to the catalog, which has the function of a database containing all the personal and medical information of all patients and the historical of their data. The catalog is located on Raspberry Pi, which posts it on another port in order to make it visible to all microservices composing the architecture. At this point, data must be shown to their end user, which may be the patient or his caregivers, or the physician. For the patient side, 2 services are available. Through TeamSpeak, on which data are updated through a specific adapter using REST protocol, the patient can visualize the data over time, while through Telegram, which takes data from the catalog through REST, he gets alarms and feedbacks about his situation. The physician instead can get an overview of the general status of all his patients through Freeboard, which takes information directly from TeamSpeak channels through REST protocol. Here we can see an example of how data are collected by sensors and sent to the iHealth Cloud. The patient is using the pulse oximeter, which is going to evaluate her blood oxygen concentration and some additional parameters. The patient has to open the iHealth application for mobile phones and follow the very simple procedure described in it. The acquisition starts straight along. When the measurement has been acquired, the app sends it directly to the cloud.
In order to get from the cloud the data coming from the iHealth devices, we created a Python script which makes requests to the correct URLs as it is specified in the documentation. First, it automatically opens the internet page where the user has to log in and give permission to our application to retrieve his or her personal data. This part is necessary because of the security procedures of the iHealth Cloud, which also require a specific certificate with a password. Then, since we have 4 different kinds of devices, we make requests in a loop, waiting 60 seconds between the requests of each data. And, as we can see in the video, which is of course speeded up, we receive data of weight, blood pressure, blood glucose, blood oxygen, and now weight again. At this point, if we open the correct folder, we can see that 4 JSON files have been updated with the actual data that is in the cloud. This is the blood glucose file, and this is the blood oxygen file, but it is the same for each file.
We developed our platform following the microservices approach in order to make it more scalable. We have 5 main microservices, and now we will explain in detail how they work. We have to remember that the results have to be used only as a support for the decisions of the user and the physician, and not as a given. For the glycemia microservice, the patient has to measure his glycemia before eating. The service takes the last measurement of glycemia and uses the patient's parameters in order to compute some suggested dose of insulin. The patient can now connect to the Telegram bot, which will ask him if he exercises and how many carbs he is going to eat, and eventually it gives back a message with the suggested dose. For what concerns the body composition microservice, the patient has to weigh himself with the smart scale so that the microservice will receive the weight value, body water percentage and fat value. In this way, it can evaluate the patient weight situation, compute his target weight and variation of fat and lean mass with respect to the previous ones. It will also check if the body water situation is acceptable. The fatigue evaluation microservice evaluates the health status of the patient during a test under stress. The patient has to measure his blood oxygen concentration before and after a 2 km run or walk at maximum speed so that the microservice can compute some parameters associated to the level of fatigue reached by the patient during the exercise. The patient will receive a feedback about his status through the Telegram service, and if the situation seems too bad, he will be asked to contact his physician as soon as possible. For the therapy evaluation microservice, the doctor has to establish the duration of the pharmacological therapy for the hypertensive patient, who will measure his blood pressure at least once a day. The microservice will consider all the values within the period of time settled and will give back a code that corresponds to the evaluation of the blood pressure trend. Through Telegram, the patient receives a message to be aware if it would be better to contact the physician. The ECG microservice analyzes the ECG track of the patient to discover 4 kinds of arrhythmias: missing heartbeats, extrasystoles, tachycardia, and bradycardia. It also gives back the duration of the RR interval and the heart rate. Telegram service will send the patient a message to inform him about the result of the analysis.
In this section, we will see the whole platform in action. First of all, let's see all the microservices running on different computers. From top to bottom, we have glycemia microservice, the ThinkSpeak adapter, the body composition scale microservice, and the ECG read, which is needed to read the serial port where Arduino is connected. On this other PC, we are running the patient registration microservice, therapy evaluation microservice, ECG post-processing, and fatigue evaluation microservice. In the end, on the third computer, we are running our 3 Telegram bots, and then from Raspberry Pi in the black shells, we can see the publisher and the code that updates and posts the catalog on Raspberry. Incidentally, we decided to create 3 different bots in order to make our platform more scalable and easier to be used by the patient. Let's now move to a cleaner screen so that we can understand better how the microservices related to the IEL devices work. The microservices that we have here are glycemia, body composition scale, fatigue evaluation, and therapy evaluation. On Raspberry Pi, we will follow what happens with the publisher and with the script that updates the catalog. For demonstration purposes, we are publishing fake data each 90 seconds in order to simulate the arrival of the data from the cloud. At the beginning, Raspberry is not posting the catalog on its appointed port, but the publisher is already working. So we can see that all the microservices receive a message, but they are not able to connect to the server and get the catalog. When we run the code that posts the catalog, all the microservices are able to work. As we are going to see now, the message is on the screen. Let's move back to Raspberry Pi. On the left side of the screen, we can see that the publisher of simulated data published 4 different messages, one for each microservice. On the right side, let's see how the updating of the catalog works. The code checks all the ports of all the microservices and sees if a new data has been added. In this case, since it was the first loop, it finds new data and we see the text catalog updated for all the microservices. But as the loop starts again, since the publisher didn't publish any new data, we see the same old data on the ports and we get the message last data already present in the catalog. In this way, we avoid overwriting the catalog and it's also more difficult to miss data. This is the experimental setup for the acquisition of the ECG signal. The patient is seated and is wearing 3 electrodes, 2 on her chest and 1, which is the reference electrode just below her ribcage, even if we cannot see it from the video. We have the electrodes connected to the heart rate monitor sensor, which is connected to Arduino Leonardo. We also have a digital button used to start the acquisition, which will last 10 seconds. Let's now move to the Python scripts involved in this process. From left to right and from top to bottom, we can follow the flow of the data. They arrive through the serial port and are posted on a specific port on localhost. At this point, the publisher takes them from the port and publishes them with the chosen topic, for the microservice that does the post-process and for the ThingSpeak adapter. As we can see on the bottom of the screen, they are received correctly. Now the microservice is doing the post-process and will print us the result on the shell. Let's see what happens with the code that actually does the update of the catalog on Raspberry Pi. Since it checks all the microservices, we have to wait for a while, but eventually we see the message saying that the catalog has been updated with the last ECG data. Let's concentrate on the ThingSpeak adapter. This part is again speeded up because the ThingSpeak adapter waits 85 seconds in order to give enough time to the catalog to be updated. In the end, we get the message that the ThingSpeak channel for the ECG has been updated. We can immediately check if this actually happened, looking on the ThingSpeak website and seeing if the Freebird dashboard has also been updated.
Here we can see that the ThingSpeak adapter receives the message sent to the glycemia microservice. Through a REST request, gets the updated catalog and sends the new data coming from the post-processing made by the microservice to the proper channel. At this point, also Freeboard will receive the last values from ThingSpeak, once again with a REST request, and will update its widget as shown. Users can connect to the Telegram bot whenever they need and ask for the service they registered to. Otherwise, a warning message will be sent. Also, in case the service has been shut down, a message will inform the patient. Telegram bot will get the right dose of insulin from the catalog based on the choices made by the patient. Here we can see how easily the physician can check the status of his patient from all his devices. If the physician needs to register any patient to our platform, a specific microservice has been designed right for this purpose. It posts an HTML form to be completed by the physician with all the required personal and medical information of the patient. Personal information includes some technical data, like the Telegram ID, in order to make the communication with the Telegram bot possible, but also the IELTS user ID, associated to the devices that have been given to the patient, and the ThingSpeak key of his assigned channel. After that, weight and height should be added, and the physician is able to choose the disease he's registering the patient for. For each disease, the physician should complete some more information needed to customize the post-processing of the acquired data. In particular, in case of cardiopathy, the physician can choose if he requires the fatigue valuation service and the ECG post-processing.
in addition to the therapy evaluation service which is guaranteed to every cardiopath. After the fulfilling of the form, the physician must press the Submit button in order to register the patient. This will trigger the activation of a post request which returns the feedback you are seeing on the screen.
With this last section, we have seen all the main features of our platform. Thank you for your attention.